Hi everyone, I'm Vanessa, and today I'm going to tell you about the Bayesian approach to measurement we've been using at our Sobeys personalization team. All right, I got two buttons. Okay, so about Sobeys and personalization there. So for those who don't know, Sobeys is a large Canadian grocery retailer. We operate different stores and banners across the whole country. We have Freshco, Foodland, Safeway, a bunch of them. And I'm a data scientist on the personalization team in particular. Our team's responsible for the system that delivers personalized offers to customers. I'm sure most people are familiar with personalization here, but the idea is, it's direct to customer offers. Offers are just for you and unique to you, and we have a variety of kind of machine learning models and things like that that deliver personalized offers to customers. Our offers in particular can be redeemed for Scene Plus points, which customers can then return for rewards like grocery cashback, movie tickets, that sort of thing. Yeah, the image on the right of the slide will show you what our personalized offers can look like. You can see kind of those are the product offers. We also have basket builder offers, that sort of thing. The life cycle of a set of offers is 1 week, so each Thursday in particular, customers are sent a new set of offers, and they have until the next Thursday to redeem them, and then they get new offers. And my current focus is on measuring the effectiveness of those offers and use those decisions, or that measurement to make decisions about how to better improve our entire system. So to get a bit more specific about that, I've kind of summarized, wait, I forgot I have two. Okay, I've summarized our measurement objectives here. So first and foremost, we want to measure the effect of our personalized offers in terms of various KPIs, key performance indicators. For people who aren't familiar, that term confused me at first too. This involves answering questions like, do personalized offers result in more customers visiting our stores? And if so, how many? Do personalized offers result in customers spending more? If so, how much? Are we making a return on investment from sending personalized offers? That sort of thing. Next, we want to be able to measure these effects across various subgroups of customers. So this basically involves answering questions like, for instance, how are customers who shop at banner A, let's say Sobeys, responding to personalized offers versus Freshco or a specific type of personalized offer? And do personalized offers bring more of our, let's say, least engaged customers to the store? Again, we do have kind of engagement groups that we've established even as part of our personalization system in terms of who's more involved with our programs and that sort of thing. And we also want to be able to measure effects across different offer variants. For instance, I mentioned the basket builders earlier, that sort of thing. And then we also want to be able to report on how credible we feel these measurements are. Like, are we confident enough in these effects we're saying to action upon these results, that sort of thing. And then, of course, we need to be able to explain and justify these results to business stakeholders. Like, we don't want to end up in a situation where we can't explain why the results are behaving in a certain way. And when you start dividing your data across subgroups, that's something you can definitely be at risk for. Why are each of the banners showing a positive effect, but overall effect is negative? We want a system that can handle that, make sense of it, and correct it if needed. So all in all, we need a measurement framework that has a fair bit of flexibility given all the stuff we want to measure, but is in no way a black box. We need to be able to make sense of the results it generates. Okay, so before we actually measure things, we need to go through kind of an experiment setup. So I've kind of distilled down the example to be a fair bit simpler here than what we do in practice. So just an idea is we're going to focus on our vanilla product offers like the one you saw in the first slide, and measuring their effect. So we can kind of reword this question of the effect of personalization in terms of like the difference between how offers perform when they are personalized versus when they aren't. So to measure this, we're going to split customers into just two groups. Treatment and control. Treatment is easy. They just receive the personalized offers. Now, our control group receives random offers. So for instance, this could result in customers getting offers that aren't relevant to them or even that kind of annoy them. Like for instance, a vegetarian getting an offer for a meat product. And quick note on why we do this. Why not just send no offers to control? And the idea is, again, that we want to make sure we're measuring what we actually want to measure. We want the effect of personalized offers, not just the effect of like any offers or a notification that, you know, Sobeys exists or whatever, right? We want to know, we want to know the effect of personalization versus not. And this way, the control offers are a sort of placebo in our experiment. Customers don't even know that they're getting them, which is good. Next, of course, we run the experiment. So the idea is customers are randomly assigned to treatment or control. It's kind of pseudo-random in the sense we do something called AA testing. Unfortunately, I didn't end up having time to include that in the presentation, but if you have questions, definitely ask me after. But basically, based on what we already know about them, we can kind of get some approximate balance based on I guess, promo week metrics going. And then at the end of the week, we observe the values of the KPIs of interest. So I've just included some examples there. Activation, have they visited the store, made a transaction, spend, how much they spent in that week with those offers. Doesn't have to be specifically tied to the offer. That's a different metric. And then now that we have the data, we want to use it to measure the effect. So that's that difference in the KPI's value, or the lift, as we can call it. And now, of course, we could just take the mean of those KPI values, but the idea is this wouldn't meet all of our objectives. First, we wouldn't have any measure of how accurate or confident we are in that, and we also wouldn't be able to incorporate the subgroups, like the engagement group you can see on the table there. So we would have to measure, like if we wanted to do engagement group, we'd have to measure each in isolation and then hope they came together to make sense, which they don't always do. So we needed a kind of framework for statistical inference that takes care of that. Yeah. Okay, so basically to kind of get into it, there's based on the title of this talk, you can kind of assume and know that we're going to be using the Bayesian approach, but before I kind of dive into what that is and the justification for our choice, I kind of want to compare it to the other common paradigm to use for these sorts of problems, which is frequentist approach to inference. This is probably the one most of you are maybe first familiar with. You're kind of in your first intro to stats class with the p-values, the confidence intervals, the significance test, etc. The root of the differences is somewhat philosophical, and there's really no need to get into that for this talk, but I want to kind of highlight some key consequences of those philosophical differences to help highlight why we're choosing Bayesian. So for starters, in both paradigms, we typically use a parameter to represent that target value of interest. So you could think of that as like the mean treatment effect and that sort of thing. And the idea is that, why did I lose my spot? Oh yeah, okay, for example, the true probability of activation or something like that, right, for a customer in a given group. So in the frequentist paradigm, this it's an unknown fixed value. Think of the population mean in statistical tests, right? In the Bayesian paradigm, this is actually considered random, not fixed. And our goal is to figure out what the probability distribution of this parameter is given the data. But first, we actually set it to an initial guess, but then we update it using data. Speaking of the data, so the data is what we observe, right? That's that table in the previous slide, encoded in a way that makes sense for a model. But in the frequentist paradigm, this is the source of randomness. You believe the data comes from some overarching sampling distribution, infinite sampling distribution, that sort of thing. In the Bayesian approach, the data is considered fixed and used to update our initial guess about the parameters distribution. It can get a little confusing because we do define a probability distribution kind of for the data, but in the overall posterior, which is what we're using for inference, it's considered fixed. Okay, so the idea about how we do inference is kind of stemmed from this idea of what's fixed and what's random. So when I say inference, I mean make conclusions about the true value of the parameter. So in the frequentist paradigm, this usually involves computing a point estimate for the parameters of interest using the data. So, and then in the Bayesian paradigm, inference involves updating our initial guess using the data. And we're going to dive more into that on the next slide. All right. Okay, so formalizing what we discussed on the previous slide, there's kind of 3 key steps to Bayesian inference. You first define a prior distribution, and that updates or to represent your prior beliefs about the parameter. And this is somewhat subjective, but you can make it kind of as objective as you need it to be. Because usually you know something about a parameter, even if you don't think you do. For example, you're often able to identify very low or 0 probability regions, like, you might know that your parameter is always going to be positive, or that it's between 0 and 1 because it's a probability. Like, that's not really saying much. And you can make it pretty diffuse, potentially, which means flat, potentially means center it. You can see it in blue in both the equation and in the kind of image that shows kind of, and it's not a perfect graph because sometimes these aren't all in terms of the same kind of thing, but it's just to kind of show you the updating procedure there in the plot on the right. So then you define something called the likelihood. Now, the likelihood is usually pretty similar to its frequentist counterpart, but it doesn't have to be. There's a lot of things you can do that would be kind of not allowed or would not fit within the frequentist paradigm that you can do in the Bayesian one. And then the 2 are combined using Bayes' theorem to create something called a posterior distribution. The posterior is in green there. And the idea is that so the likelihood and the prior update, the posterior. You also have the marginal in the denominator there. The marginal is typically very hard, or not always, but most often hard to compute, right? Because you have to essentially integrate out all possible realizations of that parameter, right? And when I say that parameter, it's typically not one, it can be multidimensional, right? So we don't actually know what it is. And the thing is, though, data is fixed here, right? In terms of our posterior, we're conditioning on it, we know what it is. So it's often, so because of this, there's kind of a family of inference kind of approaches. I ended up not having time to get deep into that here, so I just wanted to reference. Often you'll use kind of your starter, at least, is Markov chain Monte Carlo based approaches. There's a bunch of them. And then if you're having trouble with given the size of your data, et cetera, you'll move on to something else. There's that's where Bayesian can get tricky, so a warning there. But the idea is modern probabilistic programming languages will typically make this sampling pretty easy. You can just define your model, and it will then sample from the posterior distribution, and then you can use that for inference and all sorts of fun stuff. All right, so now that I've kind of introduced what Bayesian inference is, why are we doing it? Kind of highlighting now that we've just learned. Okay, so from a business perspective, you're actually able to answer key kind of questions of interest in a lot more of a direct manner. So the posterior distribution, right? The parameter, which again can kind of be defined as a function of parameters or anything like that, can directly be used, samples from that, to answer the question, how likely is it that treatment is performing control, and by how much, or what's a range of plausible values for how much? A quick note is that a common misconception here is that the p-value and by extension confidence intervals can be used to directly answer this. They can't, although sometimes it will align with the answer to this question, especially in simple cases. But the idea is, and I've heard this misinterpretation before, is that a p-value of 0.05 on a hypothesis for, say, treatment mean greater than control mean means we are 95% sure that the treatment is outperforming the control. But this actually isn't the case. So the p-value tells you the probability that you'd observe the data you just observed. Given that the treatment is not outperforming the control, meaning it's the opposite. There's no treatment effect, or not a positive one at the very least, if you're kind of doing that one-sided test. So it operates on the assumption that, that basically on an assumption conditional on theta, right, on your parameters. So the data, and the data is the random part of that equation, and conditional probabilities aren't reflexive. You can't just switch that around and then try to derive the kind of what we get from the posterior, right? The value of the parameter given theta, and then kind of do 1 minus that to get something. That's not actually how it works, right? So you can't actually get that answer. So there is less room for misinterpretation. It's kind of, I think, a bit more intuitive. Then in terms of what it also does is it encourages, I think, more nuanced decision making, because you can get a lot of different quantities from this, right? And they're pretty interpretable I find them to be, at least. So you can get, you get a whole distribution, right? A posterior distribution. You get a function of of your parameter, and then the probabilities of realization, essentially, right? So you can compute means, modes, variance, identify modality, skew, all sorts of fun things you can derive from the posterior. Also, and again, this kind of goes into the thing of can support these complex models and things that you wouldn't be able to concretely measure in the frequentist paradigm. It's a lot easier to run multiple treatment tests in parallel. You're a lot less tied to the sample size, although of course larger sample sizes do help you kind of narrow your posterior down. If you think back to the previous slide where we saw that it was kind of a lot more narrow than the prior, which was wide, but there's no minimum sample size requirements to do Bayesian inference. And you can also kind of structure your data so kind of subgroups learn from one another. So you can kind of deal with unevenness there. And we'll kind of go through an example of that to kind of solidify that later on. And you can also more easily measure groups, which is something, again, we mentioned, right? Those groups of customers, stores, regions, etc. They can be combined and compared again, an intuitive and explainable way. You can kind of drill up and drill down, right? And we're going to see an example to make that more concrete. But the idea is that this will help mitigate inconsistencies, like kind of that issue I mentioned earlier of, oh, okay, each group is going positive, but the overall effect is negative. This is something called Simpson's paradox. It can arise and can cause confusion, especially when talking to business stakeholders. So then, from a data scientist's point of view, right, or someone like me who's implementing the model, so the good thing is assumptions are explicit in the model and they're not hidden. You know exactly what you're kind of assuming about the model, what you're doing, based on kind of your priors, your likelihood, everything you see. There's no canned procedures. You build your own model from scratch and then kind of make it fit your use case. Of course, you can be wrong, but there aren't kind of this set of things you have to do. The ability to encode your prior knowledge, again, about what's possible. You can cut off certain values. If you know something's less than 100, you can put that as probability 0 in your prior, and that will eliminate it. Be careful doing this, of course, but that is something you can do. And then another cool thing is it facilitates causal inference, and due to the ease of simulation. So I didn't have time again to add this to the presentation, but the idea is it's a cool process where you can kind of basically take your data set that you've used to kind of fit your model, set one thing as constant, let's say we say the data's the same except everyone's from treatment, then do it the same for control, and then kind of get predictions from your model. You can also use Bayesian models for prediction from that, and that can give you a nice overarching treatment effect, and this is especially helpful when you have models where parameters can't be easily isolated. So I'm going to go through a quick example to kind of highlight some of the points I just talked about. So just quickly here, we have activation, which indicates if it's an indicator if the customer made a purchase, and we let yi indicate if the customer is active in any of our models. You can kind of see how that translates to the table, kind of the encoded table here. The difference in probability of activation is kind of the effect we're after, right? Between treatment and control. We want to be able to measure that overall across all customers and for each engagement group. And we're going to let mu I be that probability in the next kind of slides that show our model. Okay, so this is a simple model. Yeah, this is a simple model. For now, we're going to ignore the engagement group, focus on measuring overall treatment effect. And this is kind of the results of performing Bayesian inference, right? You'll see these kind of graphs. The one at the top right here is, or actually, before I do that, the likelihood, I just want to point out, it looks like kind of the linear or logistic regression we're all familiar with, right? And one cool thing is you can do this. It's perfectly fine and sometimes might be ideal, but you don't have to. So something we could have done here, like a different version of the same model that would give you the same results and would have the same number of parameters, is you could just get rid of beta, make alpha a 2D vector, and then have index 0, like the first one be control, index 1 be treatment, and then take the difference between the alphas to get the effect. That would do the same thing. It kind of, again, you don't have to have that slope intercept approach, and in some cases you might not want it. So going to the prior, you can see it's relatively flat on that top right-hand slide in yellowish. And then in pink, you see the posterior. So you can see how it learns from data. This is just simulated data, by the way, that I kind of made. I'll show you the real data in the next couple slides, kind of, but only when it's relevant. And then the bottom two plots show the results. So you can see, like, you get, and all I wanted to show, the numbers aren't important. It's just to show you get a full distribution. You get kind of HDIs are highest density intervals, highest posterior density intervals, and it's kind of, you could say, analogous to a confidence interval. There's also credibility intervals that are a little different, but not important for this. Or they're important, but yeah. Anyways, yeah, so adding the engagement group. Yeah, 8 minutes, okay. So we just performed inference on the pooled model. So the idea is a pooled model means that we didn't consider the difference between these groups, right? But we want to. And here we present a couple options for incorporating the engagement groups or any grouping variables, really. You can do multiple of these at once, and indeed we do, like banner, region, etc., into the model. So first option is unpooled, right? Each group is modeled separately and is completely unaware and unaffected by the other groups. So for example, the high groups alpha and beta are completely uninformed and unaffected by the medium groups alpha and beta, etc. This may or may not be desirable behavior, but we have to think in our case, right? They're all receiving the same treatments, right? They're just different people, and we just expect them to maybe react a little different, maybe, we don't know, and we want to be able to isolate these things, but we still think, you know, there should be similarities, right? So this is where you bring in something called partial pooling, which is the rightmost model. And it's also called hierarchical modeling, mixture modeling, multi-level modeling. Statistics is notorious for having a bunch of different words say the same thing. So basically, it's the same likelihood as unpooled. If you structure it this way, again, you can kind of reparameterize these in a bunch of ways. But there's additional structure added in the priors, and each group, each added in the priors. So each group has its own alpha. But those, for example, right, but those alphas are sampled from an overarching distribution, right, that have kind of a shared mean and variance. So, and the same goes for beta. So the idea is you get information about the variability between groups as well through the sigmas, but there's information sharing there. So the structure enables kind of overall trends to be learned more efficiently, and also for kind of groups to make up for one another if they're deficient in sample size or kind of doing weird things, and we'll kind of see that. You can think of it as built-in regularization for inference and stuff. All right, so also small typo here. It should say like mean results affect this in the next slide, but not that different. Anyways, so partially pooling model is in the mustard yellow, unpooled is in pink. The results were derived from the data I simulated. You can kind of see what the overall look of that data is in that purple table. The true proportions are there, that sort of thing, number of customers. And the reason why I wanted to make sure I put that there was you can see how for the high group, which is small, right, we only had, especially for control, and this is often, right, you don't want to put too many people in control, so your treatment group is bigger than control. You see kind of that there's the biggest difference between unpooled and partially pooled. And the reason for this is that, again, they're able to learn those common means, and because we're less certain about that high control group, right, because it's only 20 people, the partial pooling helps us deal with that through those shared parameters. It's going to kind of basically steer more towards that overall kind of mean, and we'll kind of get to another visual of this on the next slide. And then the other cool thing with Bayesian inference, and this is true for the unpooled and pooled cases, is in the plot on the top right there. You can kind of see how we're able to identify that multimodality, right? You can kind of see the true proportions, and again, you kind of see how that can arise in the observed proportions. And I think that's interesting, and again, maybe that is something you'd be interested in, maybe not, but it's a type of result you can get. Okay, so partial pooling, and this is the effect result. So this is like the actual difference between treatment or control. And again, it's very easy to get these things from Bayesian models because you just have these samples, you can take the difference, etc. And we're going to compare the three models we built here. The colors are the same for partially pooled and unpooled as the previous slide. And then pooled is in green at the bottom. It has no specific group effect, of course, we can't get that from the pooled model. So it's just by itself at the bottom, but you can kind of see the difference, right? And you can see how, because, again, we can't really be sure of what's going on with that high group because it's such a small sample size, especially there's only 20 people in control. There can be a lot of reasons why the results are the way they are, right? There's kind of information sharing going on there, whereas versus the high, you can see like the highest posterior density interval, and I even made this one smaller, right? It's only 89%. It's like negative 15% to or 15%, right? Like it's huge range. So it's not particularly helpful, whereas when we start to get into, we can kind of narrow that down a little bit when we use partial pooling, right? And again, these are still all relatively small. This effect becomes even better as we go on. And you can see it, again, in the population, or sorry, in the group with the biggest sample size, the low group, it's moved the least, right? Because it kind of accounts for the overall mean. There's kind of a weighting that goes on, kind of based off number of observations and consistency of those and that sort of thing when you do partial pooling in this fashion. So just wrapping up here. Okay. So the Bayesian approach has allowed us to build more complex models and deliver interpretable results that we can kind of drill down and drill up on. Hierarchical models allow us to share that information between subgroups and do all that sort of thing we talked about. And we've also been able to run more experiments in parallel. I didn't get into being able to add treatment effect. As you can see, I'm already at time. For instance, the first time I did this presentation, it was like literally more than twice as long and like way too complicated. So this is like the one that really fits. So there's lots more I wasn't able to talk about. And if you saw it in the abstract and you want to talk to me about it, definitely come talk to me about it after. But yeah, there's some examples of that, adding covariates, a varying effects model where you can correlate alpha and beta, using the posterior predictive distribution to do the causal inference that I kind of referenced. There's lots of stuff like that that you can do with these models, and they worked really well for us in our particular use case. And by the way, doesn't mean you need to do Bayesian. Sometimes frequentist can absolutely work super well. We even do it in our AA testing I referenced earlier. It's definitely, both should exist in parallel. And that's it. Yay. Thank you. Oh.
We can take one of two questions before closing. There is a mic in the middle. Oh, yeah, she's not coming.
Okay, I had two questions. Hopefully they'll be pretty fast. The first one is, I was just wondering why you picked normal priors for whatever Bayesian model or method you used.
Yeah, so in that case, I like those normal 0, 1.5 priors, honestly. The best approach to picking priors is, at least in my experience, is you see that they work for other people in kind of similar structures, and you kind of try it, and you're like, oh, that's working out nicely. And then it kind of works, and that's what you're going for. Again, you can think of a prior as almost, again, it's hyperparameters, right? We expected things to be somewhat mean-centered, just given what we've seen in the data and that sort of thing, and we can also make sense of those, right? Easiest for our business use case. So we're on the logistics scale, right? So 0 to 1.5. I actually did have a slide that had the prior predictive simulation, and you can kind of see how that translated once you took the xbit function into a pretty nice, pretty flat, distribution between 0 and 1. So basically, it does well when you kind of take it out of the logistic scale, if that makes sense.
Okay, did you also try perhaps using Jeffrey's priors?
I've looked into Jeffrey's priors. I haven't used them actually for this sort of model. I remember learning about them in school. Haven't hit them in a while, but I'll take a look. That's a good idea.
Okay, sorry, last quick question. What exact Bayesian model did you use? Is it like a mixed model? Is that what it is?
Yeah, well, mixed effects, hierarchical model. We kind of use a couple different ones for different sorts of things because we have the different KPIs, right? So, but we are going with kind of hierarchical or multi-level. Yeah, the terminology I found does get confusing. But mixed effects is one that people have heard. It's not the same as if you're talking about marketing mixture models. Those ones have a time series in them, we're doing independent trials each week is the way we've currently approached this. I have thought about that, and when we start to do offers that kind of last multiple kind of sessions and weeks, that is something we're going to probably look into. But for now, we're doing kind of these independent trials and a hierarchical model for each of those.
Okay, thank you.
Thank you. Actually, I do have the similar question, continues to the previous question. So for the Bayesian, so you said you will make some assumption of the prior distribution, right? But because the posterior distribution probably will have the same distribution as the prior, or it will be highly affected by it, right? So
Not necessarily.
have you, sorry?
Not necessarily.
Yeah.
It can influence structure. It can influence, there are cases where that is the case. There are cases where it's not. The one I did is pretty simple. So yeah, structure tends to carry over, but there are cases where that isn't the case.
So is it just because this case might be kind of simple, so you make the assumption, or have you ever tried any, there are some built-in functions you can feed your data set to different distribution, and the function will help you to pick the most suitable one, but it might be black box, so kind of hard to explain.
And actually, that is another point too, is again, the idea of having it be transparent, having things be centered in a certain way that makes sense. Oftentimes the normal distribution does work out well in these sorts of scenarios. Again, when you get into, for the parameters, right? And the overall thing we're modeling is a function of the parameters. So that's why you can see that kind of multimodality I kind of showed in that treatment effect thing when you take it across groups, right? But overall, again, we're kind of doing this for that business use case or for delivering results to stakeholders, and our generative model somewhat fits, I guess, using normals in this case. But yeah, you can debate priors like so much and oftentimes you'll get interesting things. I should mention, like if you're just comparing two groups, just go with a beta binomial, for instance. That's kind of the simplest one. That's actually a conjugate prior where you'll get a closed form for the posterior. Meaning you don't necessarily have to even do Markov chain Monte Carlo to get samples, that sort of thing. But because it kind of lent well to the mixture model and kind of showing that hierarchy and that shrinkage that shows, that's also another reason I chose it for the demo. But you get somewhat similar results, especially for means from any of them.
Sorry, the last one. So what about the partially pooled case? Because for that one, the models are hierarchical, right? So in that case, it's really hard to make multiple assumptions about them, right? So that in that case, the error might be like.
That's why you kind of assume the groups are even, right? So that's why you give you give all the groups the same priors for the alpha and beta. That's pretty common practice.